Thank you. I apologize for the aspect ratio. This bothers me immensely, but I think it will be readable. As a brief background for anyone who doesn't know what I worked on, I was the engineering manager for Facebook Paper through until very recently, actually. I've switched to the Instagram team in the past month and hope to add a lot of the sort of interactivity that you see in Paper to the Instagram app. Before Facebook, I worked at Apple on the original iPhone team as engineer number 10 and built a few of the smaller first-party apps, optimized UI kit, made the Game Center team and a few other things there. And I also went on to work at Nest Computing, which is a small startup company that taught me a lot about how compact teams develop products and work with designers and iterate very quickly. And that was very important to how Paper worked as a team. So you might have heard of Facebook Creative Labs, and Paper is actually considered the first Creative Labs application, and in many respects defined what Creative Labs is. It's actually more of a philosophy than any sort of organizational structure. There's no department that is Creative Labs. There's in fact no individual who oversees all of Creative Labs except perhaps the CEO. So there's no building in which all of these people sit. But the idea is that you have a new application that is not necessarily related to anything that Facebook has done before, and giving teams the freedom to pitch those ideas, and if they get support within the company, take them all the way to production. So Facebook is pursuing this on a fairly large scale with multiple different applications in completely different verticals, and we plan to continue doing that. One other aspect of this is that these teams are highly integrated. So they have design and project management and engineering all in the same team and working largely independently from other teams at the company. So often they will build their own infrastructure or question assumptions of the existing applications. And in that way, even if the application is not a long-term success, they build technology that are then integrated into the other Facebook applications. So today I wanted to take you on a journey of 3 parts, and I've added to the end of this as well for this audience. A little bit on the history of Paper and kind of what the impetus was for it and some of the challenges that we knew we would have going into it. And then a deep technical dive on one of the frameworks we created to confront those challenges, and also some discussion of frameworks we've made available so every public developer can use and improve their apps with. And then I'll go into some active problems that we're still thinking about and would be really interested in your feedback on, both in open source projects and just generally in discussing API trade-offs and that sort of thing. So when we started working on Paper, Facebook looked like this. And if you imagine that someone took quite a bit of time to write a multi-paragraph text post, you would easily be able to argue that this is not the best way to represent their work. And so Paper actually started from a somewhat more philosophical principle of honoring the content that users take time to create. You can imagine photographers historically have not been thrilled with Facebook, even though it has an audience that they want to reach, even if that's just their friends and family. It does not always preserve their photography in a beautiful way. So we looked at each story type and asked, how could we do this better? For a text post, that's not only making it full screen, but also making it so that if you drag on the content, it immediately expands directly in line without taking you to a different view. For photos, one interesting phenomenon in the past several years is that mobile phones have gotten much higher resolution cameras, much better optical quality in their lenses. Autofocus was introduced with, I believe, the iPhone 4. And so this resolution no longer encapsulates a lot of the detail that is accurately represented by these cameras. So we introduced a full screen photo format that you can explore by physically tilting your phone that gives you a much more accurate and detailed view into a photo that really does show you things, especially in certain photos that you literally cannot see or discern in the smaller view. And finally, there are other story types like this event that practically just fade into nothingness. They're extremely small. And yet this event might be a great opportunity for you to engage with your friends in the real world or to have a wonderful experience offline. And so we looked at these and thought, you know, most of them have cover photos. You can show a little bit of the people who are going, and more context, more links that you can get to information about that event or the people involved. So at that point, I knew that paper would require a dramatic re-architecture. None of those stories actually were very similar to what had been built before, so I was very excited to start a new application architecture. But what I was not quite as prepared for is the fact that our design team was using this new tool called Origami that had been developed for Push-Pop Press. You can go back and see the TED Talk by Mike Mattis introducing Push-Pop Press. And they have a really, in many ways, prescient interface for some of the features of paper. But the key element to Quartz Composer, which is what Origami is based on, that made this a unique challenge for the engineering team is that it was capable of implementing things often very quickly that we had no idea how to implement on mobile. They were simulations by a desktop class computer. And so it has dramatically more power available. It's not particularly efficient. You could never ship it on a mobile CPU. And in fact, it doesn't even have a traditional programming model. This is a graph solver that solves the graph every frame. And so you can put new values into the graph and count on the fact that they'll be taken into account on the next frame. So you can do very interesting things with a tool like this. Here are some of the very first demos of paper built before we had anything working from an engineering perspective. And you'll notice that there are elements that kind of change size and dynamically respond to gestures. And in the Composer demo in particular, you can see as stuff is dragged in, it kind of reconfigures the entire story. And so in seeing this, I started to get pretty worried, actually, especially about the Composer demo, because the implication of this, actually, and the designer's request is that when you're composing a post, it should always be pixel identical to what actually will get posted once the user is done. Would require that the code that renders feed is also capable of rendering animated transitions between any two possible stories. And that is actually what paper supports, and that's how the Composer works. But that was a significant software architecture challenge that took the team quite a while to solve. Then stuff like this came along. We called it Ken Turns as a funny name instead of Ken Burns. And this started to increase my worry a little bit, but I thought, okay, maybe we can one-off these cases. Maybe we can address these particularly odd features. And maybe it won't be terribly elegant, but we'll be able to build it. But then I started seeing more designs, and I realized that that definitely wasn't the case. And that this sort of, we didn't really have words for it at the time, but this interactivity was just like everywhere in the interface. And this stuff was just pouring out of Mike Mattis's brain like crazy. And he figured, you know, there's no other way to do this stuff. This is how physical objects would behave, you know, and that's the unifying principle of the application. So it became clear that we had to answer some fundamental questions before even beginning to implement the application. And so the development cycle of paper was actually about a year with a very small team working on architecture, and followed by a year of using that architecture to build the app. So it's interesting to note that current mobile SDKs make this type of dynamic interaction really difficult. The very good reason for this is that these SDKs were designed to operate on a totally different type of device, totally different class of processor, ARMv6 CPUs with the PowerVR MBX GPU. It used to be the case that literally alpha blending a few layers together could make you GPU bound. And so this kind of dynamicism was completely infeasible for other reasons. So the architecture of the system was built in a way to achieve good performance with, say, static animations like pushing a navigation controller on extremely limited hardware. And that architecture persists to this day. Now, however, iOS 7 has been changing this, introduced UIKit Dynamics. It turns out that the implementation of UIKit Dynamics has some weirdnesses that work around these limitations of the system architecture in a similar way to paper. But I'll go into more detail on the performance problems with things like UIKit Dynamics. So in any event, core animation alone is not sufficient for these type of interfaces. So what's actually more difficult now? It turns out that older UI paradigms that were more dependent on discrete taps can tolerate stalling the main thread for relatively material amounts of time, certainly multiple frames. 50 milliseconds is a lot better, but you can get away with largely 100 millisecond stall if you need to generate the view that you're going to, for example. And importantly, if the main thread is busy when a tap occurs, the tap firmware, the touch hardware, can remember and cache that tap and deliver it later when the main thread is available. But that is not true for continuous gestures. There's no buffer of sufficient size to remember a continuous gesture, and so they are simply dropped. So also, static animations are very common in pre-iOS 7 apps in particular. And what's really fascinating about these is that because they're handled totally out of process in the backboard D process you've no doubt seen, they can handle arbitrary main thread stalls. Even if you have a 3-second animation and stall the main thread for 5 seconds, in most cases it will never drop a frame. And that was really important for the original single-core phones, where an external process had to run at a higher priority in order to preempt the slow CPU, even if the main thread was busy, to get 60 FPS on the original iPhone. Now, continuous gestures are a feature of these new, more interactive type of interfaces. The challenge here is that they are processed on every frame. The touch information comes in at 60 FPS, which is intended to match the rendering frame rate. And so because of system overhead, you actually have about 5 milliseconds. Even though the frame is 16 milliseconds, backboard D still needs time to process the layer tree on every frame and do compositing. There are other things that need to happen. So you have a really small window of time before you will at least drop some of those frames, sometimes many of them. And now dynamic animations is particularly interesting because even if you initiate a dynamic animation and lift your finger and there's no longer a touch stream, these type of interactions, whether it's UIKit Dynamics or using POP, are very sensitive to main thread stalls, again, without any touch handling because they are handled in process. Unlike the backboard D style animations that are handled out of process, the out-of-process render server cannot communicate with your app quickly enough. It does inter-process communication in order to integrate feedback from your finger. So especially in this case, if you have something following your finger as though it were attached by a spring, that communication cannot occur fast enough. So again, both UIKit Dynamics and POP have an in-process loop that handles that. So our challenge number one was doing physics simulating animations at all because UIKit Dynamics was not available yet. Fortunately, we had a framework from Pushplot Press that was already pretty good at this, and that was built in the iOS 3 timeframe, so definitely ahead of its time. We made major upgrades to it throughout the course of paper. It was an active area of development for the whole project, and we recently open sourced this. This has been one of the most successful open source projects that Facebook has ever released. I think a lot of you will probably know about React, which is a very popular web framework. In a year time frame, React got the same number of stars on GitHub that POP got in a single week. So pretty big stuff. Now, unfortunately, POP did nothing at all for performance. And so if you were to use a bunch of UI views, paper would look something like this. And this is because there's just an incredibly outrageous number of views required to render this app. Especially in the minimized mode, you can scroll past a large amount of content, very large images that actually extend off the edges of their clipping region, and lots of text labels, lots of blending, lots of views to actually just create and add to the hierarchy. And so we found out that POP alone or a system like it would not be enough to implement this app. So as I mentioned before, the SDK was designed for the simplicity of operating on a single core device. The main thread was prevalent. Mobile development was a very new topic when the iPhone was launched, and of course the SDK wasn't included in the original iPhone even. And so Apple really focused on making the SDK fairly approachable, and threading is usually an inherently significant complication to that. So that was prioritized. So as I mentioned, physics simulating animations must run in process, and in particular, they must run on the main thread if you want them to remain responsive to user gestures. So if you throw an object and it's behaving as though it follows a physics simulation, and you wanted it to be able to be caught by the user and redirected, or have the user do something else while that was occurring and that thing reacted to that, it is absolutely essential that those things be done on the main thread, because that touch input is also coming in on that thread, and it will look weird even if it's off by a couple frames. So that's a major limitation. So effectively what we ran into is this constraint that the main thread needs to stall very infrequently as possible. And so the best way we figured out to do that is to do the least amount of work possible on the main thread. And so there are three major classes of things that contribute to main thread stalls. In other words, time that takes more than 5 milliseconds per run loop. So one of them is text measurement. Paper has a lot of this. There's a lot of rich text features in Paper. We do things like widow detection, which figures out if there's a word that's by itself on the last line and adjusts the margin slightly to potentially pop it up to the next line if possible, because it looks visually better that way. And that requires some extra computation. But I should stress that regular text layout is also still very expensive. It's about 1/10 the cost of text rendering, which is another very expensive thing. Keep in mind that rendering text from different languages is of radically different costs. Rendering any CJK language, Chinese, Japanese, Korean, is fairly expensive. As you can imagine, Arabic or Thai, Hebrew are even more expensive. So be sure to test those things. Images are unilaterally expensive to decode, whether they're PNG assets that are in your bundle or JPEGs downloaded from the server, especially if they're fairly high resolution. In Paper, we had these tilt-to-explore images were literally larger than the screen buffer. So the whole iPhone screen is fairly large, even if you were decoding a JPEG of that. But if you have a panorama that extends 10 screens wide, it's a really massive file. So it was essential to do this asynchronously. And arbitrary drawing, so drawing like shadows or gradients and borders and other stuff with CG also is fairly expensive. System objects are really probably the hardest one to deal with and really important not to forget. Most things in UIKit need to be done on the main thread, and even just creating a UI view, much less adding it to a hierarchy, or even deallocating one is very expensive, especially when you have lots of views. So why not just optimize all these things and make them all take less time? Well, that is always a good idea. You will save power. You will save battery life by doing that, in addition to the performance. But there does come a point where that is infeasible, or you get diminishing returns. So at that point, you really don't have a ton of great options. You can make your design simpler. You can ship a bad user experience. You can wait for a new iPhone to come out. And this was quite literally the case that we were confronting. We could tell that there were really no major optimizations left, and the app was nowhere close to good enough. So the problem constraints of doing something a little bit more sophisticated are that it should be smooth by default, which means that you can always optimize something and make it take less CPU and make it take less power. But if possible, it should always be at least smooth. So maybe it's doing a lot of rendering in the background and it takes quite a long time to actually be displayed, and you want that to be faster, but that shouldn't cause the UI to actually stall or stutter or ignore user input. Another goal is that it should be fully generalized. So we wanted to use this everywhere in the app. The main Facebook app had an earlier take on this kind of system. It's quite a bit more complex that only worked in feed, in the main newsfeed, and that's how very good scrolling performance was achieved there. But we wanted to use this in timeline and every other part of the interface. The system has these certain restrictions that we need to abide by. So it's not even very well documented. It's now been peppered in a few places in Apple Docs, but UIKit and Core Animation are substantially not thread safe. Even though CA layer has thread affinity in some senses, so if you add sublayer on a background thread, it will magically call you back on that same background thread for display and layout. Seems kind of like it was designed to be used in a multi-threaded environment. Not actually thread safe. The main Facebook app was shipped using layers in that way, and the top crashes were always related to Core Animation. so that was removed. Finally, to integrate with UIKit. UIKit provides an outrageous amount of functionality like UI Web View and UI Text Field that is totally infeasible to rewrite, and so it was really essential that those components could be integrated pretty seamlessly. So this is the view and layer relationship that probably everyone is familiar with here. Notably, every view on screen has a layer that backs it, and it automatically creates and owns. You, of course, can create layers by themselves that don't have views, but when they're connected in this way, the layer delegate is automatically set to the view, and it's expected to remain that way. So what's interesting about UI View is that it provides touch handling to core animation. So this will become more important a little bit later, but that is one of the primary reasons to use UI View instead of just see a layer. So what we thought about is, what if UI View adds features to core animation because core animation doesn't support everything that it wants, but neither does UIKit support everything that we want, so we could just do the same thing. So that's what we did, and if you create one of these third type of objects, it will automatically create a view, which automatically creates a layer. And then similar to views, where you rarely need to interface with the layer directly, we create nodes and interact only with nodes and don't really need to interface with views, although they are available, and they are also, they have property mirroring. So it turns out you can call any layer selector on a node and it's automatically forwarded. You can call any view selector on a node and it's automatically forwarded. Unfortunately, even UI View doesn't do that. So it wraps the system classes and makes them, in a way, thread safe. There's still limitations, but instrumentally, you can create nodes on a background thread, which you cannot do with UI View. You cannot even create a UI View and not use it on a background thread. The mere alloc init is not thread safe. And so that fact alone actually is what forced this pattern, because we wanted to be able to put layout code in instances so we could cache layout information, and UI View makes that categorically impossible. So what about these issues I talked about earlier that were difficult to completely optimize? How does this pattern actually address those? Well, layout is one of the hardest ones because, like I mentioned, you typically want an instance to contain your layout code. So say we have this very simple hierarchy and we want it to layout, in other words, especially take care of all of its text sizing on background threads. What we can do is just go to a background queue, create an entire story, which is a subtree, just like you might do with views, give it a model object of some kind, ask it to lay out within some constraint. And so this provides the necessary constraint for text to understand how it needs to wrap and where the paragraph boundaries will be, which is what all of the expensive stuff is, measuring the width of each glyph. And so that recurses down, and the story provides constraints to the link, and the link provides constraints to its title and its author, and that works fine. So one really nice thing about this is that you can actually do this concurrently as well. It doesn't have to be on one background thread. I'll get into that a little bit later. So as I mentioned, go to a background queue, alloc the entire story hierarchy, and just call layout. So how about rendering? Rendering is quite a bit more general than layout, or at least has a bunch of different cases. So whether it's text, images, or arbitrary graphics, they're all handled the same way. We actually receive the display call from the system. This is called on the main thread, of course. And the real code is really not that far from this. It's a little bit longer, but not much. And so we just bounce to a background queue, allocate a new buffer. Normally that's done on the main thread, which even just the memory allocation can be fairly expensive. So we can allocate the memory region in the background. Then we just call the node's draw method. So your draw method does need to be thread safe, but usually this is fairly easy, especially if the state that it uses is immutable. You have very little to worry about since core graphics itself is thread safe. And at the end, we simply jump back to the main thread in order to set, say, the layer's contents to that buffer you created. If you don't jump back to the main thread, again, you risk crashes with core animation. So walking through that same way I just did. So this is interesting in that it addresses some of the biggest costs, but some of the most maddening costs are those incurred by simply creating and manipulating UI views. For example, if you create a bunch of UI views and then add them to the hierarchy. Every time you add one to the hierarchy, it will scan the hierarchy for the first responder, asking various objects can become first responder, and then potentially promoting one. It also has a bunch of notification methods, such as did you move to window? So did you move to window nil? Did you move to a particular window? Or did a super view change? Or there are various notifications you can get from UIKit. And there are literally recursive operations that you will see very clearly in traces that back these features. It's interesting to note that core animation does not do this for the performance overhead. So we came up with a few techniques and are in fact still coming up with more to mitigate these system costs. I'm actually going to talk about the last one as well, which I didn't get to do in other versions of this. So layer backing. Here's the diagram we just looked at. So imagine that one of these boxes is a button. You have a text label inside the button, and you have the button itself. So you always simply tap the button, not the text label, or at least if you tap the area that the text label is in, it doesn't matter if the text label handles your event because it's still within the button. So it turns out that you only really need event handling at the level of the button, and you don't need event handling at the level of the label. So it would be really great if we could transparently make it the case that the label inside of the button is a layer instead of a view, because we literally need no features of the view, and the view adds significant overhead. So normally this is very annoying because the layer and view APIs are slightly different, and so mixing them is very inconvenient. And if something about your app changed in a way that meant that you did require the features of UI view, it is similarly inconvenient to back out of that. You have to change the superclass, you have to change the names of tons of calls, and it's really quite impractical. So basically nobody does that, and I would not recommend doing that. With nodes, if you enable a single Boolean property called isLayerBacked, your same class that you subclass will then just skip creating the view. You will not get any touch handling callbacks such as touchesBegan, but it will just back it with a layer. And there are various protections built in for if you call some method that only works on views, it'll assert at you. But overall, this makes it extremely easy to turn on for all the parts in your hierarchy that really don't need to be UI views. So Paper was able to reduce the number of views it created by about 50% by using this technique. So subtree precompositing is pretty interesting. There is an API on core animation called CA layer called setShouldRasterize. I'm sure a lot of you guys are familiar with this, and that API is very dangerous. It actually has no way for you to tell if you are doing something, an easy to commit error of moving one of the sublayers of that sub-hierarchy and causing the render server to constantly re-rasterize the entire area, potentially on every frame. This is disastrously expensive, and even if you're profiling your app, there is actually no tool with which you can see this occurring directly. You can do a system trace and see that backboard D is consuming a lot of CPU, but that could actually be a number of different problems, and it won't bring you directly to that issue. So again, setShouldRasterize is rarely used for that reason. In the node world, however, since we control the calling of the draw method implementations, we can build this in a way that is significantly safer to use. So for an attachment like this link, we've implemented these with an interesting JSON-based layout specification that means that we can support hundreds of different publishers with simply a designer tweaking a JSON domain-specific language for specifying where certain things should lay out, what fonts the title should be, and a lot of different properties that control how these links display. So it was very important that we implemented the actual sort of organization of this view with individual elements we could move around. However, when they're displayed, they don't need to change size or shape. And so it would be a lot better if they were compressed into a single texture. It would save memory, it would save compositing, and that is what we wanted to do with subtree precompositing as one example. So basically what this does is, again, rasterize it to a single texture. you have many, many different layers, and they ultimately get flattened. If you're curious about how this is implemented, the technique is to call each draw method and provide it a context that has been translated and clipped to whatever subregion your area is responsible for drawing, and we simply call those in the correct order and use the correct blend mode, and it works fairly straightforwardly. So concurrency is extremely important these days. Everyone here knows that all the recent SoCs from Apple are dual core. All the ones to come will be at least dual core. We can quite easily speculate. And it turns out that although simply making things asynchronous so the scheduler can help us out is necessary for smoothness in these highly interactive interfaces, concurrency will reduce wait times dramatically because you just get more CPU to work with. You can complete your asynchronous operations more quickly. So we're able to do layout and rendering in a fully concurrent manner. So you can have a multi-core CPU chewing on story layout while it's rendering text label, and then something finishes first and it starts on an image and really just pegs the CPU for a shorter period of time than it otherwise would. What's really nice about this is that these SoCs are much more efficient when you're using their full capacity than when you are using partial capacity for a longer period of time. So they will actually burn less power in total when even doing the same number of instructions if you utilize both cores. An interesting point about layout. Layout is really hard to do concurrently for a single subtree. Mozilla is trying to do this with their new web browser, but they've admitted it's a very hard problem. What we do is if you have high-level objects, such as in the case of paper, different stories that are technically independent, you can concurrently lay out multiple stories at a time. So if the server returns 10 stories, you need to perform layout on all of them. You can do that on a concurrent queue as well. So I wanted to tell you a little bit about run loop work distribution, which we shipped, I think, in paper 1.1. One of the newer optimizations, and a good example of why this pattern has proven to scale in facilitating optimizations that apply to a ton of different parts of your app sort of all at once. If you're not familiar with run loops, which are not very frequently talked about in the world of iOS, this is a very brief overview. So basically, this is an example primarily of touch handling. This is from the Apple documentation. The operating system controls the firmware for the touchscreen, and it actually, after going through a few motions to organize things, especially to determine the centroid of multi-touch gestures and stuff like this, it sends that information to UIKit by a port that is inter-process communication. So your app instance is not directly receiving the touches from the hardware, and those events then queue up. And the main run loop services those events sort of one at a time, and so it's ideal if you can process an event and return as quickly as possible. What's really important to note about run loops is that in addition to touches, they handle lots of other things, such as timers firing, custom run loop sources, delayed selector runs, various things that can take significant amounts of time. And so it turns out that the run loop, whenever it returns back, has a choice to make of what work it runs next, which is very convenient because it is built in a way that prioritizes touch handling. So it turns out that if you can get the run loop to return faster, you will avoid having a touch event be dropped if you're able to do that, even if you have more work to continue on the main thread later, just by allowing the run loop to return more frequently so it can check if there is higher priority work to do. Now, one more point about run loops. You can think of this a lot like a single thread scheduler. You can have a run loop for each thread. You can also have threads that don't have a run loop at all, but a run loop is committed directly to one thread. And the core problem with blocking the main thread and physics simulating animations is that the scheduler cannot intervene and say, whatever you are blocking the main thread with is less important than my physics simulating animation tick, because it has no purview over what's going on in an individual thread. Run loops actually, in a way, do. They cannot preempt like the scheduler, but they are much more similar to, say, old macOS, which was a cooperative multitasking environment where you could yield to the system and have it check if there's other work. this is very, very similar. So if you can't avoid work on the main thread, say you are allocating a very deep hierarchy of views and layers, you can inject spaces between, in many cases, if it's not a monolithic block, and most monolithic blocks can be done asynchronously anyway, you can inject spaces where the run loop can check for touch events. So our async rendering technology will automatically, if you enable, again, a Boolean property for a given subtree, when it's creating the backing views for the nodes, it will automatically inject these spaces for you. So even if it's a very deep and very large hierarchy, it minimizes the probability that there is a stall. So what are the technical takeaways from this? One is to not always divide and conquer. This node-based concept is actually an example of unifying problems. For example, if you were to divide and conquer this problem in typical parlance, you would isolate the text rendering and the text layout and the image decoding and so forth and try to make each of these things faster, and you can only get so far. Unifying a problem space and abstracting from there can be really, really powerful and even result in benefits that you did not anticipate ahead of time, which definitely happened here. We did not plan out all of this stuff from the beginning. Another is to accept the challenge of an ambitious design. It's very tempting to have a discussion with a designer and they propose something ridiculous and you're like, I have literally no way to implement this, no. And sometimes that's the right thing if you genuinely disagree on whether or not it's the best thing to do for the product. But if you think it would be really good, try a little harder to see if there's a really creative way of getting around the problem. And of course, don't reinvent the wheel. We really did not have the resources to rebuild UIKit, so that's very important. Facebook is really interested in sharing what we've learned in confronting some of these less trivial problems, and has been participating in open source since some of the earliest years of the company. We also want to make available more tools. We've released LLDB extensions, and like that origami tool I mentioned is completely open. And we're starting to communicate more on our engineering blog to go into technical depth on these type of topics, give tech talks, and we have discussion groups now for this sort of thing. In particular, open source is really interesting to look at in the context of this audience because Facebook until this year had not released any open source iOS code since 2009, and what was released then is a framework called 320, and 320 is really terrible. So we apologize for that, but yeah, it was actually fairly good at the time. You probably remember it was adopted very widely. It was very successful for that era. It was very early in the age of the iPhone SDK, but it did not scale very well and ultimately was not great in hindsight. So we've now open sourced 6 different frameworks from Paper, and I'll go through a few of them. KVO controller recognizes the fact that KVO is an insane API that was built in the 1980s, and it is really difficult to get right, especially in a multi-threaded environment. You have to manually unsubscribe every thing you observe in Dialog. If you don't do that, you'll get crashes or other weird issues. That's really just not reasonable, and so KVO controller will automatically tear down KVO sessions. It has much better block-based API. Fairly popular, go check it out. So we also have Shimmer, which is the loading indicator that you see in Paper. This actually works on both text and images, so it's pretty abstract. Kind of an interesting implementation. It's similar to the slide to unlock thing on the iPhone. The Tweaks framework is a built-in system that allows you to do everything from tuning a physics value and experimenting with it without recompiling. Great for giving to a designer so they can figure out all the adjustments they want. But also even enabling or disabling entire modes of the application, turning on and off features and all sorts of cool stuff. We use very extensively throughout Paper. There are probably literally 1,000 tweaks in Paper. So physics simulating animations, I mentioned POP. One thing that's really notable about POP is that compared to UIKit Dynamics, although they have a similar implementation, in other words, they are both implemented in process rather than communicating with the render server, this API is designed to be line for line compatible with core animation. So you can take a CA animation implementation and literally change, in some cases, not even the property name, just the type of the value that you're setting it on, and it will work. Whereas UIKit Dynamics, you have to buy into an entire physics model that you start simulating and you set up very declaratively. And there are things for which the UIKit Dynamics model is actually much more powerful, but the overwhelming majority of cases, it's overpowered and it's overcomplicated. We actually do not use UIKit Dynamics in any part of paper and achieve fairly complex effects. So origami is awesome for designers to use. This was essential in building paper. We relied on the design team to investigate things to a very high degree of polish and detail before we spent any engineering time on them. In other words, there are a lot of things that you should be able to tell in the design concept phase as to whether or not they'll feel good on a device or whatever the question is. And it is really good to answer those questions as early as possible and limit iteration in the technical stack, because iteration in the engineering stack inevitably results in code that is less well factored than if you know all the constraints up front and you can design it better from the get-go. It's no accident that origami is named as such. It was developed in conjunction with paper. So another cool thing is that pop and origami integrate. So it turns out that if you have physics values for springs and stuff in origami, you can use literally the same constant values in pop and they'll look identical. So the whole async thing I just talked about is actually open sourced as well. We call it AsyncDisplayKit. The main class is called ASDisplayNode. And that is currently a private beta that is certainly open to all of you guys. If you go to this URL that's been on all of these, there's a Facebook group. If you join that, we will get you access to the code. So we're doing engineering blog posts, as I alluded to. There's some other tech talks on YouTube if you're interested, and again, we're going into these groups. But one thing I really wanted to bring to this audience, and haven't really talked about to many other people, is a few points on active work that we're investigating, and random other facts that we can also go into in Q&A. The current AsyncDisplayKit does not actually expose all of paper's stuff. As you would imagine, we want to make sure the APIs are pretty solid before putting them out there. So one thing to keep in mind is this framework will be providing, in the same way that UIKit provides higher level abstractions, we want to provide even higher level abstractions. So something like multi-rep image node will take an array of URLs and it will effectively iterate over those depending on whatever conditions you've set on it for different network conditions to display a quickly downloaded low resolution image, upgrade to a higher resolution image, and do all of the asynchronous decoding and backing story replacement transparently so you don't have to worry about it. We're also working on progressive JPEG support, which will be really, really cool and help a lot so you don't have to download individual files and you can actually download chunks and partial amounts of a single file. Other patterns have proved really generalizable, but we haven't actually generalized them yet. And a lot of that is related to like loading and memory management for different types of scroll views. So I want to talk a little bit about that. So we had this concept that we named nested sliding range. And so if you think about paper's mini feed, you can scroll past a lot of stories very fast. And each of those stories has a lot of content in it. So it was very important that loading was done far enough ahead of time, which includes chunks of new stories from the server, as well as the resources such as images that each of those stories have, as well as kicking off asynchronous loading. The problem with this is that if you simply make those heuristics very aggressive, you run out of memory extremely quickly. So it was very important that we reacted to what the user did and actively tore down things that were no longer needed almost immediately when our heuristics determine that. So this is actually the only thing that is holding AsyncDisplayKit in beta. It's been stable for a few years now, and we are mainly interested in making sure that all of the tools are there to integrate it in practical applications outside of paper. And so this is what I'd love to get some feedback on. Here's how the sliding range stuff works. So the visible range, these are just names that we've given it, is quite literal. So it's whatever's on screen. It gets more interesting with the working range. So any content entering this range, which is specified in pixels, will begin actually rendering. So it will trigger a bunch of asynchronous operations to create the content. But there's also a larger range that we call preload that triggers loads from the server, such as downloading images and stuff. So you'll notice that these are dramatically biased in the right-hand direction, not necessarily to scale. So what if the user changed direction? Well, of course, we should also move stuff around and just follow what they're doing. So the idea here is that the user can move quite quickly. It's fairly unlikely they're going to go back in the other direction, or if they do, you have at least some warning with which you can move the range back in that direction and try to catch up. And so the trailing end of the range is as small as possible, as small as acceptable to preserve memory so that you can make the leading end of the range as large as possible with the remaining memory. So what's cool about this is you can actually tune it differently for different devices. So if a CPU is really slow, but you have sufficient RAM for your application, you can extend the range so that you have more time for your CPU to churn through stuff, and you don't care as much about the memory usage and different stuff like that. And as different devices come out, you can set those parameters differently. So what we found out about this, it was made for that view, the minimized feed. It actually works equally well for all types of infinite scroll views that need to load stuff. And so then we started using this everywhere in paper, like if you have attachments in a vertically scrolling story, they load and unload in this manner. If you have a photo grid, like in Timeline, same thing. And there are actually several other places. So it seems as though that most things, even arbitrary collection views that scroll for a long time, could use something like this. Now, it's especially powerful with AsyncDisplayKit because if you're using UI views, the reason that table view calls cell for row at index path only at the literal instant that a pixel of the cell is visible on screen is that you have to block the main thread to create the cell anyway, and all of the rendering is also on the main thread, so it is most likely going to stutter, at least if you have a fairly complex table. And so there really isn't any reason to create it in advance. That is no longer true if you have an asynchronous framework because you can create things in the background ahead of time, and then you run into the problem where if you only create them the moment they come on screen, they've not had enough time to asynchronously render unless you set them to is synchronous mode and block the main thread anyway. So it is much preferred to create them in advance and give them some time to render. It's worth noting at this point that Async UI should at least consider a placeholder state for the possibility that the user has gone faster than your heuristics or their device is slow, but you want to minimize how often they see that so it doesn't feel flashy. So how can we generalize this? Our parameters for generalizing it are that it should be integratable with most like table view and collection view usages, even if they weren't designed for this. So we will also assume that it is primarily intended for use with AsyncDisplayKit. I actually think the loading component of this could be useful for any UIKit app, but it's dramatically more useful for Async UI. So we have a couple options. Like we could use, we could subclass table view and collection view and add various features to them. We've pretty much decided not to do this because third parties could have arbitrary inheritance hierarchies that could conflict with that. So we're leaning towards a helper object for communicating with the controller in some way, but there are actually a couple different ways to do that. So you could imagine you could forward delegate methods. So you could set the delegate to the helper object, and it could automatically send them to your controller. Or the controller could remain the delegate and simply send the 2 or 3 interesting delegate methods to the helper object. And so I figured it'd be good to know what you guys think about the trade-off between an elegant use experience that has a semi-hacky implementation, like delegate forwarding, versus something that's a little bit more manual, a little bit more predictable, like manually forwarding 2 or 3 methods that is a little bit less magical. So please do tell us your thoughts. We are really listening. Your experience optimizing interfaces of this type would be really valuable to know about. API improvements, feature requests for any of the projects that I mentioned or any ones in the future. Again, we're paying attention to all of this stuff, so it really does make a difference. The volume is low enough that you can have a major impact on any one of these projects. Some of them are starting to ramp up, but it's not like we ignore any one of the tasks that come through. send us diffs for AsyncDisplayKit. It's an evolving framework. You're certainly welcome to contribute to it if you like. We look at pull requests just as frequently. So let me know if you have any questions. Yep, sure thing. So the question is, do you need to convert wholesale? Do you have to use nodes everywhere, or can you use them in certain parts of your interface that make the most sense and still have views elsewhere? You can definitely mix and match them. So for example, the paper interface switches to nodes at the level of stories. Of course, I mentioned they're used in many parts of the interface, but in the main feed UI, if you minimize the things at the top, that the cover cycling are also nodes, but the scroll view that contains the stories is not a node. There's no reason for it to be. It doesn't do any rendering or layout, but each individual story actually switches to nodes, and it's nodes all the way down from there. The way you can think about this is very similar to what happens if you mix and match layers and views. So it actually turns out that you can create a layer and add a views sublayer to that layer. But then you break event handling rather silently because the layer that is hosting the views layer is no longer going to forward events. The responder chain doesn't work. And so that's pretty perilous. So you can actually do something as crazy as taking a layer and adding a nodes layer to that as a sublayer. It will display. It will even lay out. It will render. It will even asynchronously render. A lot of stuff will work, but you won't get event handling. We have implemented a few things that walk the layer hierarchy instead of the node hierarchy and actually really try to fix some of those problems. So it's actually really quite a bit more reliable than if you were to mix layers and views because we walk the layer hierarchy and then back up to see if there is an associated node. So that's fairly good. But the general idea is that once you switch to nodes, which is reasonable to do at a certain point, from that point on, you should only go in the other direction. So at your leaves, you can have pure views or pure layers if you wish. That works very reliably in the way that you would expect. And as long as the hierarchy that is above the node is all views, everything will work perfectly. But other than that, it can be mixed. How does it work with auto layout? Very good question. Auto layout is a challenging API because it's very opaque. So we have banned use of auto layout in paper because there is no way to run the constraint solver off the main thread. So it will work in the same ways that UI views work. So if you don't set the frames manually, it should actually work. But you will get the main thread cost of auto layout, which can be extremely large, especially because that cost grows very dramatically exponentially as you add more constraints. So basically, if you start out with a moderately complex app and it becomes fairly complex, then it really becomes infeasible quite quickly. So it's actually a pattern at Facebook more broadly. There is only one very small project that uses auto layout.
So, I mean, the app that I'm working with, we use UI collection. So how would you nodes work with cell reuse? I mean, how do the nodes interact with cell reuse?
Yeah, it's a good question. Cell reuse is very hard. So one really interesting thing to note about this paradigm is that the views and layers that are created by the nodes are the same subclass for all subclasses of the nodes. So you can have a bunch of different subclasses of nodes. Every one of them will create a generic view and layer that are subclasses of UI view and CA layer, but they are made by the AsyncDisplayKit system, and so they're all the same type. So it's actually possible to implement a reuse strategy that involves far less developer intervention that sort of magically reuses like views in general in the abstract, where if you were to disconnect the view hierarchy from nodes when they go off screen, keep the nodes around so they cache their layout information, other properties you may have on them, and then dump the views into a pool and reset all their properties that had changed, you could then reattach those with another node hierarchy. We've tried various mechanisms of doing this. It's fairly difficult because it turns out that setting properties is actually pretty expensive. So you need to do it very accurately and not set too many properties. You need to keep track of the properties if it change. We have the infrastructure to do this, but it's not implemented right now. But it is something we want to do. So one way that we've largely gotten around the absolute need to do view recycling is the run loop amortization technique I talked about, which makes allocating and manipulating views very dramatically less likely to cause any user impact, but it is still a minor efficiency hit. In terms of orders of magnitude, the total time that it takes to do these view operations is quite small. Should not use a lot of power, but it is enough to interrupt the user experience if it's done without those spaces in between.
Are you doing anything special? You said you're monitoring, seeing which properties in the views change. Are you doing anything special to see those outside of KPO, or have you implemented your own thing?
Yeah, so what does not necessarily work very well is if you reach into the view or layer and manually start changing properties. It's much better if you have a node associated with something, change it through the node. There's actually a property forwarding system that we've done various iterations on that would allow you to set properties from a background thread and automatically batch them and trampoline them to the main thread for application to the backing objects. In fact, this is really important in the phase where you have created a node hierarchy before it has any backing views or layers. In that case, you are very likely in the init method, for example, to set up a ton of properties, and those do need to get reflected. So the way that the public version works now, for simplicity, is at the moment of mounting or creating the views and layers, we copy all of the property values that you've set on the node to that point to the backing objects as a one-time thing. After that point, we will assert if you message those property setters on a background thread, but you can still set them through the main thread. But that architecture is there, so we can easily keep track of which properties are changed. And we can also implement a more sophisticated threading heuristic. There have been various ones proposed. This is another really interesting problem we'd love feedback on to make the properties truly thread safe, even once the backing views are created. But it's interesting to note that all of Paper is implemented with this technique of before the view is realized, there's a lot of asynchronous property setting that goes on. After that, there's actually, in practice, few needs to do that. So when we made that change away from the async model, there were 5 places in the code base to port off of that.
So which kind of challenges have you faced when preparing the code for open sourcing? I assume much of these patterns require very strict discipline in use when using them. So have you changed them for the open source version to make them more safer
Sure.
and easier to use?
Yeah, it's a really good question. So the question is, have we changed the API much to make it safer and easier to use and easier to get right outside of Facebook in case it's being adopted for the first time and you don't have experience using it? The answer is not much, because the original paradigm was based on the fact that there were tons of conditions that we could easily detect and either throw an exception or an assert. So we do that very liberally. So if you don't subclass a required method or something, it will do that. If you subclass a method that is important that you, if you override a method that is important that you not override, you also get an assert. And so there are various like runtime checks and stuff at startup for your subclasses to make sure they're like conformant. So that works pretty well. There is one major design pattern that is pretty important. If you use mutable state and you have drawing methods that are called asynchronously or layout methods that are called asynchronously, you can run into race conditions of all manner. So in that case, you either need locks or just convert things to immutable. There's actually a huge trend right now on converting to immutable models. They have a lot of really beautiful properties, especially in highly concurrent environments. and this is no exception. So you need very few and usually zero precautions for making those methods thread safe if all of the data they use is immutable and unchanging. So that's been fairly straightforward. Again, things like the even the more advanced optimizations like subtree precompositing, you have to manually trigger a re-rasterization. If you move the views around and stuff inside, they just won't do anything. So it will at least be a very obvious indication that you're doing something that ordinarily would be very expensive with that option turned on. So most of the defaults were set in a fairly safe way.
I just wanted to ask about table views. Since you're doing the loading asynchronously and layout as well, can it happen that the cell goes on screen? So assume that would be a node that
yes.
The actual height of a table of a cell in the table you might actually change after you load it. That's why it's kind of simple on the main thread in UIKit because they always sort of wait till it knows the height and then it puts it there.
Right.
But the problem is that if you have some like estimated height that you put in there and then you actually know the real one, how do you manage that since UI table view doesn't have that at all? Yeah,
that's a great question. So that is if you use estimated heights and table view wants an actual height for a cell, how do you reconcile the two if they're different? This answer is a little bit different and interesting. Specifically for UI table view, where you do need to know the height, what I would recommend is that you try to create the nodes ahead of time, of course, and also initiate layout. And if the unfortunate event does occur that it comes on screen before layout, not rendering, is finished, it is actually usually acceptable to block synchronously at that point because it should have started laying out, and usually on most devices layout is on the order of 100 milliseconds for a reasonably complex view. So you may drop frames, but it makes it much simpler to deal with, and you avoid the other kind of visual artifact, which is changing height. So that may depend on how much variance you have in the height, or what devices you support. There are a lot of ways you could make that decision, but you could do it either way. A related question is how do you handle the case where rendering is not done, which is far more common because rendering is usually about 10 times more expensive than layout. There are APIs that allow you to set various types of placeholder states. And this is, in fact, a recursive thing. So you can have a high-level node that has a placeholder of an image. And you can have a sub-hierarchy that may take longer than the other things in the hierarchy to render. And you might set a constant background color for that one. If you do that, the system will automatically recognize when everything except that has rendered. I'll remove the top-level placeholder, but leave that one until that sub-hierarchy is finished. Or if that sub-hierarchy does finish, then it will remove that before the top-level one is removed, and you won't see the second placeholder at all. So you can use either an image, an opaque image, or a constant background color as the placeholder state for any subview. You can also use arbitrary UI view constructions. Anything that you can create synchronously, you can use as a placeholder. Cool. I don't know how much time we have, but
if there's any more questions.
Happy to take more of it. Sure.
Do you tend to avoid like UI view controller stuff then, or in a minute do your own view controller based thing outside of that? Because I can imagine it would have the same like forwarding problems as like nested views can.
Sure. So usually UI view controller is fine. The main problem is that you have to be sensitive to which methods you call. So you don't want to call UI view controller methods in, say, layout or display method, which would be called asynchronously. That's not very common to do, but it's definitely possible. You might want like the bounds of your view controller's view or something. Pretty reasonable, but you shouldn't do that. That's calling on a view technically, so you definitely shouldn't regardless. So usually you create a UI view controller for a fairly high level concept, and then you have your view hierarchy beneath that. So similar to what I mentioned, there's often a point in your hierarchy which you'll switch to nodes, and below that you'll either have nodes, views, or layers proceeding in that order if you do degrade. But it's impossible to have a node as the absolute highest level concept because UI window is a UI view. So it's very reasonable to have view controllers that have a UI view, and then you add a a nodes view to that. So we do that in paper as well.
Thank you very much.
Cool. Thank you.